My name is Wolfgang Lorenz from Vienna University of Technology, and it's a pleasure for me to welcome you to my presentation with the title Complexity Across Scales in the Work of Corbusier. I've divided my presentation into three parts. First part deals with the motivation and the background in general. The second part deals with the analytic method, and finally the third part discusses some of the results. The core question, the initial question was, can we call modern architecture to be smooth? And what is smoothness at all? And can it be measured? This is the initial question. And connected with this question, I have two sub-questions. The first one is whether or not the visual complexity, and visual complexity is related to smoothness, and we'll come to that point later, whether or not visual complexity changes across time, for example, for one and the same architect, as in our case, Le Corbusier. And the second sub-question is whether or not visual complexity changes across scale. Means, is there a difference if we look at the larger scales, the whole building, or the details in smaller scales? We see two buildings by Le Corbusier. They're very different from each other. The first one is Villa Schwab from 1916. It is still in a conventional classical taste. And the second one is Maison de l'Homme, or Centre Le Corbusier from 1964. So all my studies, studied 18 buildings, are in this period from 1916 to 1964. So it's all about to measure the visual complexity and to compare different facades with each other. And in order to do that, we need an adequate measurement method. And there's a fractal analysis method that seems to give us such a possibility for this measurement. In the 1960s, Louis Richardson measured the length of natural curves, for example, the land frontiers and the like. And what he realized is that the total length depends on the map of the scale he was using for measurement and the measurement device. What does that mean? It just means that he replaced the curve by a polygon of the same side length with the points located on the curve. And at the end of the day, it just had to count the number of pieces, of sides of the polygon, multiply it by the side length. And so if you use different side lengths, you got a different total length, a different characteristic, or not, it's not a characteristic value, the length. You see the difference in these two examples. The first one is a straight line. In this time, I replace it by a polyline, not a polygon, with different side lengths first. And it doesn't matter. The total length remains the same. You see that in the middle chart. From right to left, the side length decreases. And from bottom to top, the total length increases. For the line measurement, it remains the same. In this case, it's 1. Doesn't matter. Whereas the second curve is the so-called Kopp curve. It's a highly twisted curve. And when we use the same method, then we see that the total length increases exponential if you decreases the side length. And this is also visualized in the logarithmic graph, where you see a data curve with a certain slope, and while the result for the line is a horizontal line. And Richardson realized that there is a correlation between the side length and the total length, and he established the exponential law. And it was Benoit Mandelbrot, the father of fractal geometry. He rediscovered this exponential law, and related the exponent to what he called fractal dimension. And the fractal dimension is a characteristic for how much a curve is twisted. And he says as a smooth curve has a dimension of 1, it's like the line, and the more it is twisted, the higher the value is. And the value is between 1 and 2, so it can be in between. In 1982, Benno Mandelbrot introduced a method to measure the fractal dimension of two-dimensional images. And this was then redefined and modified. And finally, this method is now known as box counting method. And basically with this method, you just place a grid over the image you want to measure. It's a black and white image. And this time the scale of the grid, like the side length of the polygon, the scale of the grid is given by the number of boxes at the bottom row, or the size of a single box, for example. And then you count all boxes where you can see something of the image itself. So all the boxes are counted, that covers the image completely. And then next step, you reduce the scale of the grid, count again, and as before, you can visualize it in a double logarithmic graph. And for natural objects as well as for facades, there's only a certain range of scales where correlation between the grid size, or the scale of the grid, and the number of boxes exists. And this scale is what we are interested in. And the characteristic value is given by the slope of the regression line of the data curve in this scale. However, with the box counting method, a couple of influences coming along. For example, you have to be aware of what you are measuring. You are not measuring the original elevation, you are measuring what's on the plan. So what are the significant lines, for example? You have to be aware about the line thickness, width of the line. Then the starting position of the grid, the reduction factor, and so on. And finally, this was the reason why I've developed my own program in VBA for AutoCAD and established a whole set of measurements with different parameters. So what are the values now, or the results of such measurements? For a single measurement, the algorithm tries to find the largest range of scales, so grid size, where the coefficient of determination is very close to 1, which means a very high correlation between these two values. This is what we're looking for. And then we have this, the scale of the range of scales, and we have the characteristic value as the slope of the regression line. As I said before, there are so many influence factors that we need many different measurements with different parameters so that we can say that there is a characteristic value. And for this, we use another statistical values that's visualized in the box plot. Here we have the interquartile range and the median. These are the important values now. And finally, the range itself is given as a ratio between the grid size and the height of the building. So the largest grid size and height of the building, the smallest. So coming to the results. So if I'm looking at the single measurement, there are two possibilities. First, that as I said before, the range, we see a data curve that is straight and have a very low derivation, so the coefficient of determination is very high, or it's very close to 1. But there's another possibility. This is this one, where I have a sharp band in this data curve. So this clearly separates two different ranges. One with a higher visual complexity or higher value, fractal dimension, and the second one with a lower one. And this could already be observed with other buildings like Haus Tugendhat by Mies van der Rohe or the Haus Steiner by Adolf Loos and this kind. Then there's a second possibility to compare buildings by comparing all facades of one and the same building. And either all of these facades have a similar fractal dimension or similar visual complexity, or they differ from each other. So we have 2 by 2 possible outcomes when we combine these characteristics. Going to discussion. What we see here are all results for all buildings that are measured and all elevations ranked by year from left to right. And initial question was, is modern architecture called smooth? And smooth is a term that we find in relation with fractal geometry and architecture. And it is in most cases given by the number 1.3 or below. I wouldn't say that this is really their number, but this is a range. Yeah. If it's lower, then we may call it smooth. However, we see that there are many above, even above 1.5. It's a very high visual complexity. The first one I remember is Villa Schwab, which is still in a more classical days. So this is a value that we have expected before, but the other one, not in this sort of outcome. The second question was, does it change over time? And as we see, this is ranked by time, by year. It does not. It comes up, down, so it's very diversified. I would say modern architecture, this is not similar, similar to an outcome from when I measured buildings by Adolf Loos, because there you have no tendency like here, no tendency at all, and we can really conclude that modern architecture of the first and second generation may not have a clear tendency to lower values or whatever. And the third one, does it change over scale? Yes, for those where we have this sharp bench in the data curve. And this is visualized here by one and the same elevation. You get 2 values, one for the first range and one for the second range. And these are connected with this gray transparent box. Coming to conclusion, the method itself is suitable to compare different facades with each other in respect of visual complexity. We can say that modern architecture has many facades, so it's very diversified. There's no relation between year and degree in this case of Le Corbusier. And this is important, but we can not make any statement about the quality. It doesn't say, is it better or it looks nicer or not. It's just makes a statement about the visual complexity. And there are two questions for the future work. The first one is, why happens this sharp bend in the data curve? Is some special architectural elements responsible for that? I can't answer that yet, but hopefully in the future. And the second is, why are some facets of one and the same building changing? Is it because of orientation, outer influences like privacy, street view, garden view, side view? This thing will be focused for the future.